Hello, my name is Scott Howe. I'm Senior Director of Customer Success at Movelis. I'd like to talk to you today about advancing power telemetry. As the size and complexity of artificial intelligence models increases, it's necessary to both optimize the hardware through architectural innovations, as well as focusing on optimizing the power delivery and voltage being applied to these ASICs and SoCs. Movelis as an IP company focuses on three distinct planes or product families. Firstly is Ionic Insight, which is our sensor family and which I will be discussing today. The Ionic Power involves on-die voltage regulator technology, which allows you to optimize the voltage per core or per processing element inside your ASIC without having to rely on independent ball and PCB regulators to optimize the power for each core. The Ionic Generate family is a very long-standing and flagship product family of ours, which is involved in clock generation IP and droop response systems, which is a combination with one of our sensor products. The theme for today's presentation will be that you have a very difficult time identifying the voltage that is actually appearing at the transistor level. What's shown here are actual oscilloscope captures from a test chip that we developed. On the left, you see the voltage that's seen outside the ASIC on the test board by probing the voltage regulator going into the package. On the right-hand side is what's actually going on inside the chip. The key here is that there are drastically different characteristics on these waveforms, and it is the on-die or at transistor voltage waveform which defines your performance, your yield, etc., depending on where you are in the product lifecycle. At each stage of the product lifecycle, from ATPG on the tester, functional workloads in the field, and even extreme handcrafted scenarios such as virus workloads, each requires a different Vmin set point. This is the minimum voltage that you can apply external to the chip, which will still allow proper functionality, i.e. the critical paths on chip will not violate setup. On the tester, running either at stuck at low frequency or even at speed has different characteristics for this Vmin set point. If you are running stuck at vectors where every transistor, every flip-flop in the chip or sections of the chip are transitioning at exactly the same time, you can have very large DIDT events causing huge voltage excursions. In the field, you may have less deterministic alignment of transitions, but you also have less control or less awareness of what workload is being run on your IP or your AI core. Varying workloads can draw significantly different amounts of current and have significantly different switching characteristics. And finally, the virus workloads are handcrafted patterns which are intended to provide or create the worst case realistic or feasible workload that could occur and cause the largest transitions on the supply. As I mentioned earlier, the theme is going to be what is going on inside the chip at the transistor versus what you see outside. So you're applying a Vmin set point on your PCB or your tester with a lot of decoupling capacitors to filter the supply, make a nice clean DC level. However, on chip at the transistor level, you may see a waveform such as this. The rising edge of the scan clock causes many, many millions of transistors and flip-flops to change at the same time, which pulls a significant amount of current, and through the inductance of the package and resistance of the package, causes a very large droop on the supply. Similar behavior would happen on the falling edge or other edges of the actual scan clock. Again, the key theme here is what you see outside at the voltage regulator is not what's happening at the transistor. And we'll talk later on about what the consequences of these large excursions can be. Functional workloads vary with time, vary with space, location on the chip. Even for the same frequency, you can have fairly drastically different IR and droop events on chip. And again, the handcrafted worst case scenario of the virus workload can cause a significant droop on the supply. Conclusion here is that the Vmin set point at the voltage regulator needs to be determined and set based on a variety of factors, both the platform, the time, the location on the chip, could even be the temperature. And to measure the waveform on chip requires very fast nanosecond resolution timestamps on the data that you're gathering. Otherwise, you may miss a very fast, sharp droop event. And you want a reasonable level of accuracy on the y-axis of the actual voltage at a given time. We'll discuss PDNs throughout the rest of this presentation, power delivery network. This is the path from the voltage regulator on the PCB through the package, which has its associated inductance and resistance. It may have on-package capacitors, decoupling capacitors, to help with supply noise filtering. And then on to the die itself, silicon die, and it has its own distribution paths through the inductance and resistance of the routing to the transistor on the chip. Today, there are several visibility challenges. As I mentioned earlier, various locations on the die itself, various locations in the path from the PCB to the transistors. And then there's a temporal aspect where the voltage behavior, voltage at the transistor can change drastically with time based on workloads, based on other environmental conditions. One of the key activities that's needed to optimize the power and performance of an ASIC is to optimize your voltage frequency curves, i.e. what frequency can you run for a given applied external voltage. These tables of voltage and frequency combinations will vary based on the platform, and it's very challenging without having visibility at the transistor level to understand what external voltage you can apply to achieve a certain frequency, or what is causing failures at a given applied voltage. And so what this leads to is either over-margining, where you're raising the supply too high and wasting power. Recall that the power equation for power consumption is CV squared F. So it's a square function of voltage. So every millivolt of over supply translates to a significant amount of power wasted. So you may be over-margining because you don't have visibility as to what's actually going on and wasting power. Under-margining could have the opposite effect. You could be on the tester throwing out good die simply because of excessive supply bounce, which is not realistic or representative of what you're going to see in the field. So you could have a DPPM hit because of under-margining. Or in the field, with given workloads, you may have the failures of your setup paths, your critical timing paths, which occur periodically. And you're having to simply raise the supply because you're having some paths fail because your nominal was too low. Also, we need to consider the packaging and context for the chips themselves. Single monolithic die, the traditional single piece of silicon in a single package, has the challenges we've mentioned so far. These die in themselves are getting bigger, larger, and have different process temperature characteristics across the die. So for a given core copy that you have arrayed throughout your ASIC, you may have significantly different performance temperature process at various corners or various locations on your die. Therefore, you may need to optimize your Vmin on a per location basis. Extrapolate that to reticle size die, where you have as large of a die single die as you can get from a given reticle. This simply exacerbates the problems I mentioned earlier about having large arrays. Now you can have larger arrays or larger cores that are tiled. And even within a core itself, you may have variation. So you may want to be getting visibility into the voltage behaviors at various locations throughout even a single core. Finally, if you package multiple die into a chiplet environment, a multi-chip package, you either laterally connected, stacked, but what you find here is the environment that you use to characterize your die on the tester is drastically different than the environment that's actually being used once you package multiple die into a chiplet. So having voltage visibility at each of these scenarios, especially at the chiplet post-packaging time, because the voltage that's being applied to the transistor in a chiplet environment may have had to go through through silicon via packaged dies, may be generated by one of these dies. So what you tested for on the tester may not be what the transistor is seeing in the field. So we have increasing spatial variation, increasing current densities, perhaps thermal densities as well. And again, as always, the workload is transitioning from static to dynamic. Higher inductance on some of these packaging technologies will lead to larger supply bounce and excursions. So during the various stages of the life cycle of a piece of silicon, you need to have different VF curve optimizations. On the tester, you'll have a certain power supply, power distribution network to get the voltage to the die, a certain inductance, a certain socket resistivity, for example, which will cause you to need a VF table for AT. This will be different from what you see in the field, because you will have a different, perhaps soldered versus socketed scenario, different decoupling environment. On the tester, you may have access to a lot larger decoupling capacitors on the test board, whereas in the production in field, you may have restrictions on component sizes or component counts or costs. And in between, you have production tests where you need to actually optimize so that you do not over or under margin. Again, over margining, you might pass failing die because you have so much extra voltage, or you may fail good die because you have such a low voltage at the die, which is unrealistic relative to what it would see in the field. So here's an example of various droop or voltage excursion responses based on workload. Here we have the virus workload, which will have, by definition, the largest excursion on the supply. And then you have two other example workloads, which have their own characteristic pattern of current consumption and therefore voltage bounce. And in all of these cases, drawn here in red, is the Vmin at the transistor, which is the voltage at which your worst case timing paths will fail. So it's necessary in this type of a scenario, if you expect your virus workload to be feasible, you would need to set your VDD at the virus level, so that if that workload ever occurred, you would not violate setup. It is obviously up to the ASIC manufacturer to define an acceptable level of potential failures where you do not want to burn this excess power to accommodate the virus workload, which may or may not occur, but also have the consequence of being able to identify scenarios where you actually violate the setup voltage. So that's another application of the visibility at the transistor level of the voltage, to be able to identify that you have passed a critical voltage threshold and want to respond accordingly, whether it's dump the workload and reload. But knowledge of that is important. Otherwise, you could be processing bogus data. Again, on the tester, screening false negatives or failing parts, which are good parts because you have too much voltage droop on the supply, an unrealistic voltage droop, or over-margining the supply and passing devices which would fail in the field because you've over-margined on the tester. So here you are optimizing the cost function, which is the defective parts per million, without visibility into the actual supply at the transistor inside the chip. You won't know what the voltage actually is, and therefore whether you have a VRM level on the PCB that is too high or too low. So in the chiplet environment, again, having a VF curve at wafer probe time based on the characteristics of the supply power distribution network and the voltages at the transistor. After packaging, having another package device test, having a different PDN, having a different testing environment, perhaps with a socket on an ATE versus a wafer probe card, will have a different VF curve family. At each stage of testing, you will need to have a VF table that is used, and also, ideally, having characterized the VF curve, have continuous monitoring to ensure that it is actually indeed achieving the desired voltage at the transistor. As the process changes, as wafer lots change, you want to be able to gather data and continue to monitor. And finally, out in the field, once you've deployed your chips into your racks, into your server clusters, you want to make sure you maintain visibility at the actual transistor level. Aging effects can come into play over hours, weeks, months, years, and being able to see a change in the characteristics at the transistor is very important. So electromigration effects, which could cause an increase in supply resistance, could cause larger voltage drops over time, and without visibility at the transistor level, you're not going to know. So Movelis has a product called the PDN IQ IP. This is an IP which has two pieces. One is a controller, and then a very tiny sensor head, which can be placed at your desired critical location to monitor the supply. It could be the weakest point in your PDN. It could be the most active part of your processing core. What this gives you is real-time nanosecond timestamp visibility into the power supply voltage characteristics. The IP has a trigger manager, which can be used to begin the storage of waveform data, again, on the nanosecond range. There is a trace buffer to store the waveform characteristics. There are several telemetry aspects, being able to indicate when triggers have happened, how often they've happened for data gathering. APB and JTAG interfaces for data readback. And mentioned earlier, there's a very tiny sensor head itself, which provides data to the controller block. This allows you to have transistor level PDN visibility or voltage visibility wherever you need throughout your core. Here are some examples of how you might be using the PDN-IQ IP. You have a certain droop, and perhaps you're triggering off of the lowest voltage excursion. You're going to, as shown in yellow, you're going to capture the waveform around that trigger and be able to read that back, perhaps correlate through your cross-trigger matrix with what else was going on. Did you load a certain aggressive workload? Is the temperature at a certain critical level? But by being able to timestamp the data that you can read out of the IP, you can correlate that to other events that are occurring on your chip. And here again is perhaps another even more extreme excursion on the supply is going to cause a retrigger and a recapture of new data. There's many factors which could be used to initiate a trigger and a data capture on the IP itself, including external factors that you can define. So in summary, Movilla's PDN-IQ IP allows you visibility at the nanosecond timescale and millivolt accuracy on the y-axis of the voltage at the transistor. This is very useful to provide visibility at each stage of the silicon lifecycle, from testing through package testing, through field usage and monitoring. Chiplets are the extreme case where the power distribution network in the field packaging is vastly different from what you see on a wafer probe or at the package door or die level testing, single die level testing. At each stage, you require voltage frequency characterization, and knowing the voltage at the transistor is paramount to being able to create accurate and useful tables of voltage and frequency combinations. And visibility at the transistor level through your power distribution network, it encompasses the entire life. The usage, the value may be different on the tester for DPPM optimization versus in field for early failure detection. But in all cases, being able to see and understand the voltage at the transistor level is critical. Thank you for listening.